Okay, let's start talking about higher order derivatives and concavity and the second derivative test. First, let's get ourselves warmed up with regard to taking higher derivatives. So the first thing we want to note is how you'll see the notation of higher derivatives. Okay, so far we've just been finding the first derivative, and we've denoted that as f prime. We're going to denote the second derivative as f double prime. So this is going to be notation used for first through third derivatives. And you're accustomed to this notation f prime of x. You've also seen dy dx. And you've also seen this notation, perhaps. Okay, well, as we move to the second derivative, you would have f double prime of x. You would write it as this d squared y dx, indicating the second derivative with respect to x, and this also should have a square. Or you might see it as this notation, and you can see this superscript, the 2 indicated. Okay, and you would do this likewise for f triple prime, and then you would change these superscripts to be the third derivative if we're talking about that. Where it becomes more interesting is where we talk about n greater than or equal to 4, where we're talking about n being the derivative. And we would denote that as f and then a superscript in parentheses. And so if I were talking about the fourth derivative, you would see f and then the superscript parentheses 4 of x, and that's saying the fourth derivative. Okay, that's actually quite different than having f to the fourth x. Okay, that's not the same. What you're seeing here is the fourth power. It means actually taking f of x raised to the fourth. Okay, the fourth power. All right, so just some notation, and let's warm ourselves up, and let's talk about higher order derivatives. Okay, so what do I mean by that? Well, if you can take the derivative of a function, which we should at this point of almost any function, we've got all those rules, then I could take the derivative of that derivative, and that would be the second derivative. So let's find f double prime of x for each of the following. Let's make our first one be a polynomial. So I've got 5x to the fourth minus 4x cubed plus 3x. I'm finding f double prime, so in order to do that, I'm going to take the first derivative, which is, using that power rule, 20x cubed minus 12x squared plus 3. And then the second derivative, which you see the notation there, the double prime, all I have to do is take the derivative of the first derivative. So I'm going to have 60x squared minus 24x plus 0, which I don't have to write. So we can see all I've done is I've taken the derivative of the first derivative. That would be my second derivative. Okay, so if I have my first derivative, all I have to do is then take a derivative of that, and that'll give me my second derivative. Let's remember when we have radicals. So I've got the square root of 2x squared plus 9. It says to find f double prime. So in order to even take the first derivative, you're going to have to remember to use these rules that we've had, and let's rewrite our function in some way that we can manipulate it to use a rule. And so I've rewritten f of x by raising that quantity 2x squared plus 9 to the 1/2, so that when I take the first derivative, which I indicate with the prime, I'm utilizing a chain rule. So I'm going to multiply that power to the front 1/2, rewrite the quantity, which is that inside function, 2x squared plus 9, and then I'm going to reduce the power by 1. So 1/2 minus 1 is negative 1/2, and then you multiply by the derivative of the inside function, and the inside function is 2x squared plus 9, and its derivative then is 4x. And so you can just clean this up a little bit nicer. 4x times 1/2 is going to give you 2x, and that would sit on the outside of this 2x squared plus 9 raised to the negative 1/2. And you realize that there are things that we could do to make this look a little bit different, such as getting rid of this negative exponent. But what I'm trying to do is actually to find the second derivative, and so I've done as the first. And when I start to take the second derivative, I look at this and I say, okay, it's not just chain rule anymore. I'm going to have to utilize the product rule. And if you recall, we have first times the derivative of the second plus the second times the derivative of the first. And so what I mean by that, here's the first function. So I'm going to do first times the derivative of the second. Well, the second function is going to be using that chain rule. So I'm going to put a little dot here because this is the first times the derivative of the second. And the derivative of the second function would be, multiply that negative 1/2 to the front. I rewrite that inner function. I reduce the power by 1, so this is going to be a negative 3/2. And I multiply by the derivative of the inside, which is going to be a positive 4x. So I've got first times the derivative of the second, and I've got plus the second, which is this function. I'm going to rewrite it. Pardon the mic there. I'm going to rewrite that second function, which is the quantity 2x squared plus 9 raised to the negative 1/2. And I'm going to multiply by the derivative of the first. And of course the first is the function 2x, and its derivative is 2. Okay, so what would we want to do to clean this up a bit? Well, let's see what we can do. How about we go ahead and multiply the 2x times the 1/2. So it'll give me just x. X times 4x is going to give me 4x squared. Oops, and I wonder if you caught this. I should have had a negative, so this is going to be a negative x times 4x, so negative 4x squared. Okay, so I've done this. And then I'm going to have that quantity, which I can't multiply into. This is under a radical. And then over here, I'm going to have plus 2 times the quantity 2x squared plus 9 raised to the negative 1/2. So we talked about a moment ago that how could I rewrite this? Well, this is the second derivative. Let's make this look a little bit nicer. Let's get rid of these negative exponents. So I'm going to have a negative 4x squared, and I'm going to move down here this 2x squared plus 9 to the 3/2. I'm going to have my plus the 2, which is over 2x squared plus 9 raised to the positive 1/2. And I go, this probably could be rewritten as a single fraction, so let's find our least common denominator. It looks like our least common denominator would be this 2x squared plus 9 to the 3/2. So that's my LCD. We're going to get a common denominator. So I go, well, this fraction can stay the same, this rational expression. However, over here, I want it to have the LCD where if I multiply it creatively by 1, that the denominator is going to end up being 2x squared plus 9 raised to the 3/2. That's going to be the LCD. So I need to figure out what this equivalent fraction would look like. And so how can I get this raised to the 3/2? Well, if I think about just multiplying like x squared and x cubed, when you multiply, you're simply adding the exponents, right? You do that without thinking. You're like, oh, that's x to the 5th. So what I want to do is multiply this in such a way that I have to the 3/2. So basically, I'm saying if I had x to the 1/2 times x to some power, I want it to be raised to the 3/2, which means what am I going to add to make the exponent 3/2? So 1/2 plus what gives you 3/2? Well, I can simply say that would be 2 halves, right? 1 half plus 2 halves is 3 halves. So that means what's missing right here would be a factor of 2x squared plus 9 raised to the 2 halves. Well, 2 halves is the same thing as the first power, so we don't have to write it. So if you agree, we would keep that 2x squared plus 9, and I would add the exponents. 1 half plus 1 is indeed 3 halves. So if I'm going to multiply it down here, I can't just change the problem. I have to multiply it in the numerator. So all I'm doing is creatively multiplying this fraction by 1. And so I'm going to rewrite this so that now I have an LCD. That first fraction is going to stay the same because it had the LCD. I now have multiplied by the quantity 2x squared plus 9. So I'm going to have 2 times the quantity 2x squared plus 9 all over 2x squared plus 9 raised to the 3 halves, because I have multiplied these to get the LCD. And so now all I have to do is come down and make this fraction come together. So keep that common denominator. That's how you add fractions. I have a negative 4x squared, and here I'm adding 2 times 2x squared is 4x squared, and I'm adding 18. And so hopefully you're looking at this and saying, oh, that can cancel out, right? I'm going to be left with 18 over the quantity 2x squared plus 9 raised to the 3 halves. And that would be our answer for our second derivative. All right, let's continue doing the same thing. Let's find the second derivative, but this time let's work with this exponential. So our function is going to be 6e raised to the 3x, which is raised to the 4th. So 3x to the 4th. Okay, so in order to find the second derivative, I'm first going to have to find the first derivative, which we've been doing comfortably for a while. So f prime of x, I'm using the constant rule, where I'm going to maintain that 6. And then I'm going to take the derivative of e to the 3x to the 4th. So I'm going to first rewrite our 3x to the 4th. And then, because the derivative of e to the x is just e to the x, so you take the overall derivative, and then it's applying chain rule, which says let's multiply by the derivative of what's considered our inside function. So what we've done is we've replaced what's usually an x up here with this 3x to the 4th. So now I take the derivative of this, and I'm going to have 4 times 3 is 12, 12x to the 3rd. And so now I can rewrite this as moving the 12 times 6 as 72 x cubed e raised to the 3x to the 4th. So this is my first derivative. Okay, now I'm going to find my second derivative as asked, but when I take my second derivative, I'm going to realize that this is product rule. Okay, so see if you can do that on your own, maybe pause it. Product rule says I'm going to do first times the derivative of the second. So the first is going to be 72x cubed. And I'm going to multiply by the derivative of this e raised to the 3x to the 4th. So you rewrite e to the 3x to the 4th. I multiply by the derivative of this function in the exponent, which is going to be 12x cubed. And so I've gotten the first times the derivative of the second, which we'll clean up in a moment. And then I have plus the second function, which is e 3x to the 4th, times the derivative of the first. And what's the first? The first is just 72x cubed, so the derivative of the first is going to be 3 times 72. So pull out your calculator or jot it down on a piece of paper. That comes out to be 216. I reduce the power by 1, so 216x squared. And so I'm going to have 72 times 12 Cleaning this up, 864. I've got x cubed times x cubed. I'm going to add those exponents, get x to the 6th. I carry down my e raised to the 3x to the 4th. And then on this back end here, I'm going to have plus 216 x squared e to the 3x to the 4th. Okay, now what else could we possibly do? Maybe factor out a GCF. Make sure this looks like an exponent here. So I can factor out the GCF, or I could just leave it. You could be asked to continue this and maybe find like f double prime of 1 or f double prime of 0, and then you would just go in and substitute for your x values and find it. Okay, so now that we've talked about higher order derivatives, let's get back into connecting what we were talking about earlier on with the first derivative test. So what I've put in front of you is a graph, and we've talked about having a relative max or a relative min, and so you could see that this would be a relative max where I'm pointing, and this would be a relative min. And we've talked about if I take and look at, let's maybe call this A, and over here B. These are the x values A and B. If I look from A to my relative max, I can see that my function is increasing. And we talked about with the first derivative, and I'm going to see if it calibrates okay. If I want to draw a tangent line to this point, and you can see it's just slightly non-calibrated, but if I'm drawing a line tangent to this curve at this point somewhere between A and B, at least on the segment where my function is increasing, we can clearly see that we're tracing from left to right and moving up. You can see that the slope is positive. So this is a tangent line with a positive slope. So our first derivative is increasing. If this is our relative max, I can see on the other side of this relative max, my function is now decreasing. And if I want to draw a line tangent at this point that I'm just now drawing, I can see that the slope of that tangent line, or the first derivative, is clearly negative. Okay, so we've talked about that. And I could likewise do the same thing down here where we're talking about the relative minimum. So we've discussed some things and we worked through where we've said, well, if f prime is negative, then f is decreasing. But if f prime is positive, then f is increasing. Okay, well, it turns out that we can actually go a little bit further in depth, and let's describe these regions, and I'm going to trace it here in blue, where our function, let me undo that, where our function would be holding water and spilling water. So if you think about pouring water, and again, I'm not quite calibrated here, so I'm getting close as I can. If I think about looking at this graph, the portion that I have here in blue would be where my function would be spilling water. Think of a bowl, it's spilling water. And so we'd say that this is concave down. And for this green portion, it holds water, we would say that it's concave up. Okay? So new terms that we're discussing, concave down means that the function spills water. And it's concave up, characterized as concave up, if the graph holds water. Okay. Okay, so let's think about this portion of the graph that is concave down. or even, well, let's look at the green one where it's concave up. And let's think about drawing some tangent lines on this curve. So if I draw a tangent line here, or I draw one here, what's happening to the slope? So we're getting a steeper and steeper slope as I am increasing, right? So my slope is increasing, which means my first derivative is increasing. So let's think about the fact that we now know how to take a second derivative, and let's parallel what we have learned about the first derivative and our function f. So if now I'm talking about the second derivative, I now can indicate what's going on with the first derivative. So let's say that, I apologize, but I was interrupted, so I'll hopefully edit this out. We'll see. But what I was saying here is that our first derivative is actually increasing. So let's say that we know that our first derivative is increasing. Well, what does that mean about f double prime? So I've lined them up so that you can parallel these. Well, if I know that f prime is increasing, then that means I know that f double prime, its derivative, should have been positive. Likewise, if I get that f prime, looking at these tangent lines here, if I draw on that side, that it's decreasing, that means that f double prime should be negative. Well, how does that help me? Well, take a look at this. I've got these increasing tangent lines for the portion where I am concave up, and I've got these decreasing tangent lines for where I'm concave down. So what does this mean for me? It means that I can tell you about my function f and its concavity. So I have that if f double prime is positive, then the function f is going to be concave up. And if f double prime is negative, then f is going to be concave down. Now remember, I'm working off of what's happening to that first derivative to talk about the second derivative, and all this synthesizes and makes up what we know about f. Okay? And so one easy graphic to do would be, I'm going to indicate by making like eyes, would be to say I have taken the second derivative, so this is second derivative and it's positive, so I did two of these plus signs because I'm talking about the second derivative. The second derivative is positive, and so I know my function is concave up. Whereas if I take my second derivative and it's negative, so two negative signs here talking about the second derivative being negative, my function f is concave down. Okay? So if the second derivative is positive at a point, we're concave up. If the second derivative is negative at a point, we're concave down. So now we're going to use everything that we know about our first derivative to start talking about the second derivative and figure out concavity. Now it turns out that we have a point at which we change concavity, and that is called the inflection point, or the point of inflection. Okay, and if you recall, when we talked about the first derivative, we would see where we're increasing and decreasing, and that change occurred at a critical number. I was talking about an x value, critical number. And we would find the critical number by taking the first derivative, setting equal to 0, or seeing where it doesn't exist. And so in order to find the point of inflection, which is going to be an x-y coordinate, we're actually going to set f double prime equal to 0, or C, where f double prime does not exist. Okay, so our task is now to find all intervals where our function is concave up or down, and all inflection points. So let's take a look at our first function. Let's do f of x is equal to x to the 4th minus 8x cubed plus 18x squared. And so what we're going to do is find the inflection points first, and then we're going to go through basically the same process that we've done with the first derivative test. So in order to find inflection points, we're going to have to take the second derivative and set it equal to 0, or find out where it doesn't exist. Now this is a polynomial, so the first and second derivatives are going to exist everywhere. So I just need to get to that second derivative. So this is a 4x cubed minus 24x squared plus 36x, which means that the second derivative is going to be 12x squared minus 48x plus 36. And so to find my inflection points, I'm going to take f double prime and set it equal to 0. So I'm going to have 12x squared minus 48x plus 36 set equal to 0. Remember, this derivative, second derivative, is going to exist everywhere we have a polynomial. And so because this is a quadratic, I should have some quadratic methods. So I'm going to factor out a 12. I'm going to have 12 times quantity x squared minus 4x plus 3. And then I'm going to factor, and this would factor into, let's see, two numbers that multiply to 3 but add to negative 4. So it's going to be x minus 3 and x minus 1, right? Which means that x either equals 3 or x is 1. So it looks like I have 2 inflection points. And so if I want to find out what the point of inflection is, I'm doing all this to learn about the function. I'm going to find f prime of 1, and then I'm going to find f prime of 3, so I can get the point of inflection. And so if I go through that, hopefully I come up with the right answer here. It'd be what, 1 comma, is that 11? And if I want to find f of 3, go through, plug this in, hopefully come up with 27. And so I have 3 comma 27. So these are my points of inflection. Okay, that's what it looks like. All right, now I want to determine the concavity of my function. And so remember, these points of inflection are where our function is changing concavity. So what we're going to do from here is basically like what we did in the beginning parts of chapter 13. Instead of critical numbers placed on a number line, you're going to place your inflection points, your x values that is, and you're going to test it into your second derivative. And what you want to do is use that factored form, and so that when we come down here, when I test, I'll be able to determine what's going on with f. So if I plug into my second derivative and I get that the second derivative is positive, according to that smiley face, if the second derivative is positive, we are concave up. If it's negative, we're concave down. And so we're going to test some x values. How about x equals 0, x equals 2, and x equals 4? We just need to test something in between. So if I plug in x equals 0 to the first set of parentheses, I have a positive from that 12. I have 0 minus 3 is going to give me a negative. I have 0 minus 1 is going to give me another negative. So I get an overall positive, which means my function is concave up. If I plug 2 in, I've got 2 minus 3, which is negative. I have 2 minus 1, which is positive. positive times a negative is a negative. A negative second derivative tells me that my function is concave down. I'm also going to do this for something on the other side of 3 to the right. And so I'm going to plug in 4. 4 minus 3 is positive. 4 minus 1 is positive. A positive times a positive is a positive, and so my function is concave up. So I've got my points of inflection, and now I can say that the function is concave up anywhere I test from negative infinity up to 1, and it looks like on the interval from 3 to infinity. My function is going to be concave down anywhere between 1 and 3. Okay, let's do the same thing for this function. It's a rational function, so the first thing you probably want to notice is the domain, and you know that x cannot be negative 1. So negative 1 is not in the domain of this function. Okay, you cannot divide by 0. All right, so I want to find the intervals of concavity and inflection points. So I know I'm going to take the second derivative, and I'm going to find where the second derivative doesn't exist or where it equals to 0. So let's first start off by taking the first derivative. Well, if I want to take the first derivative, I'm going to need to rewrite this function so that I can use, rather than the quotient rule, maybe chain rule. So if I rewrite the function as negative 2 times the quantity x plus 1 to the negative 1, I use chain rule, which says negative 1 times negative 2 gives me a positive 2. I rewrite x plus 1, I subtract 1 from the power, so the power is now negative 2, and I multiply by the derivative of the inside function. Well, the derivative of x plus 1 is just 1, so I don't need to actually show anything here. When I take the second derivative, I'm using chain rule again. I do negative 2 times 2, which is negative 4. I multiply by that x plus 1, now raised to the negative 3, and again multiply by that inside function's derivative, which is 1, so I don't have to write anything. What I may wish to do is change this into a form where I no longer have negative exponents. So I've got negative 4 all over the quantity x plus 1 cubed. Now this is what I want to set equal to 0 and what I want to see where it doesn't exist. So if I set f double prime of x equal to 0, what I'm doing is I'm taking negative 4 all over x plus 1 cubed, and I'm setting equal to 0. Now this essentially is a fraction. Any x value I plug into this left-hand side will be negative 4 divided by something. Negative 4 divided by something else. Negative 4 divided by 100. Negative 4 divided by 800. Negative 4, whatever it is that I plug in here, it's always going to be negative 4 over a number. So perhaps if I don't realize something right away, I go about my business as I say, well, I'm going to multiply both sides by the LCD. Right? This is called eliminating the fractions. And I get negative 4 equals 0. Well, that can't happen. Right? There's actually no way that this fraction could ever evaluate for any x value I choose to be 0, because it's going to be negative 4 divided by a number. So f double prime will never equal 0. So I'm not going to have an inflection point contributed from taking the second derivative and setting it equal to 0. So what I'm now going to do is I'm going to investigate the other thing, which is to see where does f double prime not exist. Okay, well f double prime is negative 4 all over the quantity x plus 1 cubed. Where would it not exist? Well, let's think about it. It would not exist if the denominator is evaluated to 0. Well, when does that happen? Well, that means that x plus 1 cubed would equal 0. So that's saying that x plus 1 equals 0, which means that x would have to be negative 1. So it seems like if x is negative 1, my second derivative doesn't exist. But we actually said that negative 1 is not in our domain. Right? It's not in our domain. So if I realized it from the beginning, I have this vertical asymptote. Right? These asymptotes exist with these rational functions where the denominator would evaluate to 0. what I'm going to do is I'm going to see what's going on either side of the asymptote. So it's not that we have an inflection point, it's just that we need to know what's going on around it. So there's no inflection point or point of inflection, but I do have this vertical asymptote that I need to see what's going on either side. So instead of putting my inflection point on a number line, I'm going to put this x equals -1, and I'm going to see what's happening on either side. Okay, so we're going to test, how about x equals -2 and x equals 0. And we're plugging it in to our second derivative, which is -4 all over the quantity x plus 1 cubed. And so it's basically like this template is what I call it, is if we can figure out what the sign is of f double prime, we're going to know about the concavity of f. So I want to know what's going on. If I plug in -2 to the second derivative, well, the numerator is a -4. It's going to stay that way. If I plug in -2 to the bottom denominator, -2 plus 1 is -1. I cube -1, I still get a negative. So negative over negative is an overall positive. Well, if f double prime is positive, we've determined that f is concave up. Well, let's go on the other side of this asymptote and let's see what's happening. If I plug in 0 to f double prime, that numerator is still just a -4, so I'm going to have a -4. If I plug in 0, it's going to be 0 plus 1 cubed. Well, what's 1 cubed? It's a positive, so I get an overall negative. So I have that my function f is concave down. So I have no points of inflection, but the function is concave up from -infinity to -1, and it's concave down from -1 to infinity. Okay, well, how is this so? Well, if you have a pretty good graphing calculator, you'll be able to figure it out. If you take a peek at it, and we put in that, make sure I have the right one here, yep. If we put in x being -1, here's my vertical asymptote, and I should know also that there's a horizontal asymptote because that degree in the numerator, the degree 0, is smaller than the degree of the denominator. That means I have a horizontal asymptote. So I got my vertical asymptote. I have a horizontal asymptote at y equals 0. And I have that my function is concave up from -infinity to -1. And so my function is going to look like this. This is concave up, we would hold water. And this is concave down, where we spill water. And that is our function. And it should make sense. There's no point of inflection.